amount of momentum a football player has is proportional to his mass times his velocity. Which has more momentum, a football with a mass of 0.4 kilograms moving at 26.8 meters per second, or a football player with a mass of 90.7 kilograms moving at 4.47 meters per second? Let's do it together. We know that the football has a mass of 0.4 kilograms and a velocity of 26.8 meters per second. The equation that we'll use is momentum equals mass times velocity. We're looking for momentum, and the equation is already arranged for momentum, so we can just plug our numbers in and solve for the total momentum. The momentum of the football is 10.72 kilogram meters per second. Let's do the same thing for the football player. We know that he has a mass of 90.7 kilograms and a velocity of 4.47 meters per second. We'll use the same equation, momentum equals mass times velocity. We know his mass and his velocity, so we can plug our numbers in. We find that his momentum is 405 kilogram meters per second. If we compare the two momentum, we can see that the football player by far has more momentum. You might have thought, since the football had a greater velocity, that it would have a greater momentum, but we have to remember that we consider both mass and velocity when we consider momentum. Which would you rather have to catch, the football or the football player? I'd choose the football too. If an object's momentum changes, its mass or its velocity has to change. Newton's second law in terms of momentum tells us that the force you feel is proportional to how quickly your momentum changes in time. When your momentum changes, it's usually your velocity that is changing, so the force you feel is dependent on how quickly that velocity changes in time. Somewhere we see this in our everyday lives is inside of a car. If you try to brake in a very short amount of time, then the force that you feel will be greater. If you try to brake in less time, then the force that you feel will be less. If we rewrite our original equation, we can see that the net force times the change in time is equal to our change in momentum. We call this net force times the change in time the impulse. If you're traveling in a car at 11.2 meters per second and you want to stop in 2 seconds, what force will you experience? What if you stopped in 4 seconds instead? For the first case, we know that the initial velocity of the car is 11.2 meters per second, your mass is 60 kilograms, and the time is 2 seconds. We will use the expanded equation for force, and since we're looking for force, we don't have to rearrange it at all. Plugging in our numbers for the initial velocity of 11.2 meters per second and a final velocity of 0 meters per second, we can solve for force. The net force would be 336 newtons. In the second case, the only thing that changes is the amount of time. We will use the same equation and plug our numbers in just as we did before, and find that the resultant force is half of what it was before, which is 168 newtons. When you go to take your driver's test, remember that the force you feel significantly decreases with the amount of time you take to stop. This is also one of the reasons why we wear seatbelts. Without a seatbelt, you would be forced to stop by hitting the windshield in a very short amount of time. With the seatbelt, it increases the amount of time that it takes you to slow down, therefore you won't get as hurt. In the example of the car's change in momentum was the same, because its mass didn't change, and the change in the velocity was the same in both instances. That means the impulse changed only dependent on the amount of time that changed. If we want the force to be small, then the change in time has to be great. If we want the force to be big, then the change in time has to be small. In both cases, the momentum is the same, but the consequences are different. If you were jumping down from a wall, would you want a small or big change in time? If you didn't want to go to the doctor with broken bones, you'd probably want to have a big amount of time. The next time you're watching a football game, driving a car, or doing anything that relates forces and velocities, I hope you look for examples of momentum, because they're everywhere.